Well, hello, students. It's Mr. Rich. It is Sunday night. We're getting a little bit of an early start tonight. It is about 3 minutes until 8 o'clock. And tonight I'm going to work some of your homework problems. I've received a few from some students that I'm going to work. If you've got some problems that you want me to work, you can send those to me at askmrrich@gmail.com. And I think I've got my email here. So there you go. So that's my email address and my phone number there. So if you need to reach me there, you can use that email address. Well, what I wanted to do tonight is I want to start off with one topic that I wanted to discuss that was kind of on the thumbnail for tonight's live session, and this was why effort wins in math. And kind of a subtitle is why being a math person is really a myth. And I want to talk about, what I hear pretty consistently from students and from some parents. They'll say that I'm not a math person, or my student or my son or my daughter isn't a math person. And I want to be very clear up front. That sounds kind of like a harmless thing to say, but really it's one of the most damaging beliefs that you as a student could carry with you. Not because it's negative, which it is, but things can be true and also be negative, but just because it's wrong, because math success has very little to do with where you start and almost everything to do with how much consistent effort you put in through time, over time. And that is just true about so many things in life. It's really not about it's not about where you're starting. It's about what you do consistently over time and almost on a daily basis. And I've been a teacher for quite a number of years, and now I'm no longer in the classroom, but I do coach students every day pretty much. And students come into my math classes and into my tutoring sessions with very different backgrounds. Some had great teachers in their prior classes. Some have great teachers now in their current class. Some had some bad teachers in some of the prior classes, or they might even have a not so good teacher right now. Some remember those topics that they learned, even if they had a good teacher, but some forget like most of what they learned in the past. But here's the key idea, that math is cumulative for sure. I mean, you do need to learn as you're going through each of your classes, but our brains are adaptable. What matters isn't really what you know right now at this moment today, but whether you're willing really to do repeated work on what you don't know yet. The brain doesn't really care where you start. It's going to respond to repeated effort that you put forth. And this idea aligns closely with a philosophy that's been popularized by Carol Dweck, a very famous psychologist from Stanford, I believe is where she's from. And that is that the ability of our mental capacity grows through sustained effort, not fixed traits that we are born with or that we acquire. It's through the effort that we put forth. And so when you struggle with math, you're trying math problems and you're getting frustrated. Your brain really isn't saying, I can't do this. This is impossible. What it's saying is this information is unfamiliar to me. And every time you work through a hard problem, your brain is literally strengthening the neural connections. It only happens with effort. For example, watching solutions doesn't make these neural connections, or reading notes doesn't do it, but doing the actual work and struggling does, right? This is why I encourage students, sure, use maybe YouTube videos to help you learn, but you've got to be putting pencil on paper and actually putting forth the effort to try practice problems. When I coach students, for instance, on the ACT and SAT math section, I'm assigning them 2 to 3 hours of work between the sessions for them to work on, because even if I know that they could only get half of those right, I want them to try them. I want them to think about those problems and put forth that mental exercise, that effort mentally to try to figure those problems out. And then when we get together, I'll coach them on the ones that they missed or the ones that they just had to give up on because they couldn't figure out. What happens sometimes is we find out there's some gaps from their prior learning that we have to go back and fill in. But I need them to put forth that effort, and then I coach them through the solving of those problems, right? Give them a tip, and then maybe they can work through the next step. And then I give them a hint so they could get to the next step. So I know them putting forth that mental effort, not just watching me do the problem, but them doing the problem with maybe a little bit of coaching. That's what's going to establish those connections that they need in their brain. So struggling is what is going to make you a better math student. So students who improve the most aren't the fastest at doing math, but they are definitely, I have found, going to be the most persistent. They are going to put forth effort consistently over and over, almost, I'm going to say, on a daily basis. Now, so why? Well, let me say this. What does it really look like? Like when I say put forth effort, that doing the work on a consistent basis, what does that look like? Now, I'll say what it doesn't look like. It's not just grinding for hours and being miserable as you can't do problems. I mean, that definitely is not something that's going to help you. But what real effort looks like is short, consistent practice over time. 30 minutes a day is, I think, a good prescription. It's a willingness to get problems wrong, to do them maybe how you think they should be done, and then you check your answers later. It's a willingness to acknowledge what past concepts maybe that you don't understand and go back and fill those gaps in. And I realize sometimes we don't know what we don't know. However, that's where kind of the next step is that you have to be able to ask questions, and instead of just getting confused, but ask questions to seek clarity. So you can ask questions of your friends, of your teachers, of your friends' teachers, who maybe if they have a different math teacher, you go talk to them, from a parent, from ChatGPT. You can interact with ChatGPT as a virtual tutor. You can go to YouTube and do a search and try to find a video that might explain the concepts to you. So you have to really be, you have to be an investigator, right? You have to be somebody that's willing to seek out that knowledge, to seek out the help, find what it is that you don't know, and then dig deeper and deeper until you can find understanding. So I say 30 focused minutes a day where you're putting forth effort. It's going to beat 3 hours of panic once a week. So it's over time. And I will tell you, those of you who exercise, who maybe are very fit, and that's part of you, who you are, is you understand that that is a little bit every day, consistently over time, yields great benefits, great results in your strength and your conditioning. And it's not something that you do once a week. It's something that's almost on a daily basis. And not that you have to do 3 hours a day of exercise and fitness training, but 30 minutes, 1 hour, maybe once a day. That's what's going to pay off over the long term. So here's really the truth that I do want to leave you with tonight. You don't become good at math and then get motivated and then put forth the effort. What you do is you put in effort because you know what it is you're aiming for. You know what a good math test score is going to yield, and what a good math grade in a semester is going to yield, or what a good SAT score is going to yield for you in terms of what your future goals are. And that's what eventually is going to make you good at math, by you putting forth that effort, because you know what the end goal is going to be for you. So if you're willing to show up, to struggle, to stay consistent at your practice and seeking out help and understanding, then your starting point really becomes irrelevant. All right. That's kind of the point. And that's really not just a motivational talk. That's neuroscience, right? That is making the connections in your brain to get to where you want to be. Well, what I want to do next, moving on from that, is I want to answer some homework questions. So I'm going to share my screen and work a few problems here. So let me throw up the screen that I want to share. And let's see if we can get this up here. Okay. So let's get over to our first question here. So someone did send in a geometry problem that I wanted to work here. So this right here is a geometry proof. Now, a lot of the geometry students now are in similar triangles, proving triangles to be similar. And so here we've got two triangles, and we are trying to prove that triangle EAB is similar to triangle DCB. And you can see in the figure here, this proof statement that we're trying to prove, that little squiggle there means is similar to. So what we'll start with is our given. We're told that angles EAB and DCB, angle DCB, are right angles. All right, so that's our given. Now, what I definitely want to do, so EAB, we'll go ahead and mark this up, and angle DCB are right. Now, I do know, before I even do this proof, that I am going to include the fact that those two angles are congruent. And I know that I also have two angles here that are vertical angles, and that those have to be congruent angles because they are vertical angles. So I already know that I'm going to use angle for this proof. Now, if you're just joining me, my name is Mr. Rich, and we are working through some homework problems that my students have submitted. I'm working on a geometry problem right now. If you do have a math question that you want me to tackle here during our next, we got about 50 minutes left in this session, you can send it to me to the email address that you see on the bottom scroll bar, askmrrich@gmail.com. And I will keep that email open, and I'll be looking for any emails that you send in. Okay, back to our proof. So we do have our given. Now, what I'm going to say here is that angle EAB, I'm going to actually say the measure of angle EAB is 90 degrees. And I'm going to say that the measure of angle DCB is equal to 90 degrees. So I have to apply a numeric value to those angle measurements. And why do I know that those are 90 degrees? Well, we're just going to say that that's the definition of a right angle. Right? When they tell me it's a right angle, I have to go ahead and be very explicit that a right angle is something that's equal to 90 degrees. So now what I know is that these two angles measurements are the same. So I can say that the measure of angle EAB is equal to the measure of angle DCB. Now, what would be my reason for that? Well, the reason that I'm going to give for that, I'm going to say that this is substitution. Although I could, yeah, I'm just going to go with substitution. Is that since I'm going to plug in, since they're both equal to 90, though, that means they are equal to each other. But I think that's going to suffice to say that's substitution. But remember, it's not enough to show that their angle measurements are the same. We want to show that they're congruent. So I actually have to make this statement that angle EAB is congruent to angle DCB. And that's just the definition of congruence. So we'll write that down. So that's one of the pairs of angles that I need to use the angle definition for similarity. So I've got one of them, but then I'm going to have to say here that angle ABE is congruent to angle DBC. All right, those are the two vertical angles, and that is just going to be the theorem of vertical angles. Vertical angles happen to be congruent. And now I can go ahead and conclude this by saying triangle EAB is similar to triangle DCB, and that is because of the angle-angle similarity theorem. All right, good enough. Let me see if we have anything that has come in. So let's take a look here. Right. If you do have a question for me, ask mrrich@gmail.com is going to be the email to send that question to. And if not, I have a few others that have come in before me. So before the session started tonight, and it looks like I don't have anything that has that's come in yet. All right, so let's go to the next one. All right, so this one was from a pre-calc student. So some of the pre-calc classes in, well, I would say all of the pre-calc, AP pre-calc classes in St. Johns County, they've moved into lesson 3.12 in unit 3 of the trigonometry unit, which has to do with trig identities. I think it's called equivalent trigonometric expressions is what the actual lesson is called. But what it is it's taking some, in this case, it's taking a trigonometric expression and trying to find one that would be equivalent to it. And the way that we do this is we use what are called trigonometric identities. And there is a list of trig identities that that you should know as a student. And I'm going to go pull up the list of trig identities and show those to you, or at least the ones that you're starting with. And here is the list. So there are a lot of trig identities, but the ones that we really start with and the most important, at least in the very first part of lesson 3.12, are these right here. So we have a ratio, two ratio identities for tangent and cotangent. So tangent of an angle is going to be the sine over cosine, and cotangent, which is the reciprocal of tangent, then therefore would be the reciprocal of sine over cosine. So it's cosine divided by sine. So if it suits our purposes when we're trying to solve an algebraic, or I should say a trigonometric equation, or trying to prove an identity or simplify a trig expression, sometimes we want to do some replacements. Or I could replace tangent with sine over cosine. Or maybe I see a sine over cosine and I want to replace it with a tangent. And so what you do here at any given step is going to depend on what information you're given in your identity or in your expression. I'll show you some the example here. Most of the trig students know these reciprocal identities. So I'm not going to go into those, right? Sine, cosine, and tangent. You have to know what their respective reciprocal functions are. And then down here are the three, what we call Pythagorean identities. So here is the most famous or popular Pythagorean identity. Now, why is it called the Pythagorean identity? Real quick, if you consider the XY coordinate system and you consider a circle that's centered at the origin, what we know is that when you come out here to a point XY on that circle, this X coordinate, if that's R, this is the adjacent side, which is the X coordinate, and this is the Y coordinate. Well, think about this. If this is the angle theta, that Y coordinate is going to be associated with the sine function, because that Y distance, that vertical distance from the X axis, is the opposite side of the triangle. And so if this R if this is a unit circle that has a radius of 1, then this Y coordinate over here is the sine of the angle, because it would be the opposite over the hypotenuse, where the hypotenuse is 1. The X would be the cosine of the angle. So therefore, if you apply the Pythagorean theorem to this, that gives you sine squared, that's the one leg of the right triangle, plus the square of the other leg, which is cosine, that has to equal the square of the hypotenuse. And the hypotenuse of the unit circle is 1. So this is that trigonometric identity. Now, these other two Pythagorean identities come from the fact that we can just divide this one identity by sine squared or by cosine squared. So if you divide this on both sides by sine squared, this becomes a 1. cosine squared over sine squared becomes cotangent squared, and 1 over sine squared becomes cosecant squared. If you take the sine squared plus cosine squared equals 1 and you divide by cosine squared, well, if you divide this by cosine squared, you get tangent squared. Divide that by cosine squared, you get a 1. 1 over cosine squared is secant squared. Okay, so you have to know and commit to memory all 3 of those. I tell my students, just memorize this, write it down on your test at the very beginning of the test, and then derive those 2 at the very beginning so you can look at them. I'll show you why that's important, because when we take a look, let's go back to the problem at hand here. When I see cosine squared minus 1, I am thinking about the sine squared theta plus cosine squared theta being equal to 1. So one thing that I know is that I can create a cosine squared minus 1 expression out of this equation on one side. If I move the 1 over and make it a minus 1, I move this 1 over to the left, and at the same time bring the sine squared over to the right, it becomes a negative sine squared theta. So what is this cosine squared theta minus 1 equivalent to? It's equivalent to negative sine squared theta. So my next step in this process would be to call that first part negative sine squared theta times secant theta. Well, I know what secant theta is. It's 1 over cosine. So what I could do is I can say that this is sine negative sine squared times 1 over cosine theta. When I look at my answers, I think what I like is answer B, and I will tell you why. Because I could rewrite this as a negative sine theta over cosine theta times sine theta. And this is tangent theta times sine theta with a minus in the front. And so I'm going to go with answer B. Now, that's not the only way that we could have come up with B being our answer as an equivalent form of what we were given. There's multiple ways that we could have done it. I'm just showing you one. The point is, we do it through a repetition of substitutions. All right, going back to see if we have any questions that have come in. No questions. Let's go to the next one that a student had submitted. And again, this is a pre-calc student. So the figure above shows a circle of radius 5 with an equilateral triangle PQO. Which of the following gives the coordinates of point P? All right. Now, what we do in our answer choices, if we look at these different angles, this angle on the unit circle does look like 2 pi over 3 radians. This one looks like pi over 3 at point Q. Now, what that means is I can get rid of 2 answers that I think are just not going to be possible here. 5 pi over 6 would be this angle over here. So there's no way really that that's going to get me the answer that I want. And also 4 pi over 3 is down in the third quadrant down here. Okay. And so we will get rid of that. But now you have to be very careful with a problem like this. The tendency would be to just automatically go with answer C. Okay. However, you do know that point P, it's going to have an X that's going to be negative, and it's going to have a Y that's positive because it's in the second quadrant. So when you look at this, 5 cosine of pi over 3. Well, cosine of pi over 3 is positive, and 5 is positive, obviously, and a positive times a positive. This is going to give you a positive X. Sine of pi over 3 is going to be positive. So this can't be our answer because I need a negative positive. Now, cosine of 2 pi over 3 is going to be a negative value because cosine is going to be negative when an angle here terminates in the second quadrant. So that's going to be my answer right there. Now, okay, so I'm not going to go into much more detail on that. I'll leave it there. Now, let's go down to the next question. This says, for the periodic function, a portion of the graph is shown. Given that f of negative 2 is 3, that looks to be about right there. So there's f of negative 2. Find the value of the period k. Right, so they want us to find the value of the period k, and you can see that all of my answers, I'm choosing between a period of 12 and a period of 16. Now, when I look at this periodic function, I'm given a maximum value here, it looks like. I think I can assume that this thing is going to be doing something like this, and I'm given a minimum value. And you need to know that if you can measure the horizontal distance along the x-axis between a max and min, that is going to always be 1/2 of a period for that function, for that periodic function. That distance is obviously 8, from negative 4 to 4. So therefore, the period has to be 8 times 2, or 16. So we can get rid of A and we can get rid of D because I need a period K of 16. Now, it says, what is the ordered pair on the graph of f when n is equal to 2? What they've given us here is this notation that shows us that if n is an integer and k is the period, that the y values are repeating every period. So that if f of negative 2, I'll show you what I mean. If we know that f of negative 2 is going to be equal to 3, and it is, they told us it is, and we see it on the graph. If the period is 16, that means that if I go 16 horizontal units to the right, which would put me at f of 14, I have to have the same y value because it repeats itself. Or if I even go now another 16, that puts me at f of 30 or f of 46, right? As I keep going in chunks of 16, because the period is 16, I will stay at the same y value. If I went 16 units to the left of negative 2, that would put me at negative 18. That would also have to be a y value of 3. So you can see right here that my answer is going to be f of 30 is going to be equal to 3 because of the periodic nature of the function and the period being 16. And I think this is, I have 2 questions that did come in from my Calc AB students. And this right here is what we'd call an antiderivative. And what this is asking us is, what function would I have had whose derivative would have been 3 plus secant x tangent x? So what we do is we will take the antiderivative of both of these terms separately. So the antiderivative of 3 is 3x. Now you have to consider, back when you were in last semester, when you're learning about derivatives, which trigonometric function had a derivative that was secant x times tangent x? And the answer to that was secant x. Okay, so this is 3x plus secant x. And then we always add a constant at the end of an antiderivative, because we know that if we take the derivative of a constant, that constant its derivative will be 0. So there really are an infinite number of functions whose derivative is this, and they all differ by a constant at the very end of that function. Now, the last one that I want to do. So this is what we call a definite integral. We could have called this antiderivative here an indefinite integral because it had no limits here, right there. Whereas this problem, as you will see, there are x values that are limits that we have placed at the top and bottom of our integral. So what our job here is to take the antiderivative of this and then evaluate it at both the upper and lower limits and subtract those. It's called the fundamental theorem of calculus. So let's first of all do this. Let's use our properties of integrals, and we'll bring the 2 constant out to the front. So it looks like this. And those limits are from negative pi over 4 to pi over 4. Now let's take the antiderivative of secant squared. So we have to consider what function, when we took the derivative, gave me a derivative of secant squared, and that was tangent. So this means that we would have 2 times tangent of x, because this antiderivative would be tangent. Now we're using theta, so we'll go ahead and put tangent of theta. And then what I'm going to do is I'm going to put a vertical line and then re-establish these limits, negative pi over 4 to pi over 4. So what I'm doing now is I am going to evaluate this antiderivative at both of these upper and lower limits and subtract them. This is called the fundamental theorem of calculus. So it's 2 times tangent of pi over 4 minus 2 times tangent of negative pi over 4. Right? So I am evaluating my antiderivative at the upper limit of the integral, and I am subtracting the antiderivative evaluated at the lower limit. Now, what is tangent of pi over 4? Well, tangent of pi over 4, that's first quadrant angle, pi over 4, and it's equal to 1. So this is equal to 2 times 1. And then I have a subtraction. Now, what is tangent of negative pi over 4? So if you consider the unit circle, negative pi over 4 would be where you've rotated clockwise down into the 4th quadrant, and the tangent right here is going to be equal to a negative 1 because you're in the 4th quadrant. So this will be minus 2 times a negative 1. So this answer is going to be a positive 4 is what that is going to be. And that is our answer. Okay. Now, what did we really just do right there? Those of you that have taken calculus, you know that what we just found is the area underneath this function bounded on the left by negative pi over 4 and the right by pi over 4. Now, what I want to do is I want to go ahead and show you in Desmos what that looks like. So I'm going to do that. I'm going to come over here, open up Desmos, and let's graph the function 2 secant squared theta. So let's graph this. So y equals we don't want a capital there. So y equals 2 secant x. Now I'm going to raise this to the 2nd power because it's secant squared. So we'll do secant squared. And then I'm going to bound this function on the left at x equals negative pi over 4, and on the right at x equals pi over 4. So what calculus does for us, and those of you who are in calculus and have been paying attention, you know this, that this number 4 is representing the area that is bounded at the bottom by the x-axis, the top by the function 2 secant squared x, and on the left and right by negative pi over 4 and pi over 4. So that exact area right there is the number 4. And that's what we just found out. Okay, students, that's going to be it for tonight. That's all the questions that have come in. Just doing one last check. So no more came in. I will be here next Sunday night at 8 p.m. And if you need me to answer your homework questions, you can do it by sending me an email at askmrrich@gmail.com. gmail.com. I will see you all next week.